Okay, so today we shall do matrix decompositions. We'll begin with the most fundamental decomposition, which is the, the LU decomposition, and then we'll do PLU, which is just an extension of the LU decomposition, and then we'll do Cholesky decomposition, which also is very similar to the LU decomposition. So we look at the three matrix decompositions. LU decomposition, so this is what it looks like. We have a matrix, a square invertible matrix of dimension n. So it's an n by n matrix. And what we do is we decompose this matrix A into this form. L is a lower triangular matrix and U is an upper triangular matrix. So this is what the LU decomposition looks like. This is the given matrix A, and we decompose, that is, factorize this matrix A into two factors. One is a lower triangular matrix L, and you see in this matrix we have the diagonal elements L11 to LNN, and the lower triangular elements are not all zeros, but the upper triangular elements of this matrix are all zeros. That's why this is a lower triangular matrix. And the second factor here is U. The diagonal and the upper diagonal elements of this matrix U are not all zero, but the lower triangular elements of this matrix are zeros, all zeros. That's why we say that it's a upper triangular matrix. Visually, this is what it looks like. What is shaded white corresponds to zero. Okay, this is the original matrix A, the non-zero elements everywhere, and then this is the lower triangular matrix. Its upper triangular elements are zero. This is the upper triangular matrix. Its lower triangular elements are zero. This might be a little misleading because the diagonal elements in both cases also are non-zero. Okay, here's an example. I have this 3 by 3 matrix, 1, 2, 2, 4, 4, 2, 4, 6, 4. Okay, now what I'll do is, this is what I'm going to do. I will use step 1. I will use the first row, 1, 2, 2, or A11, A12, A13. I'll use this row, and then using that row, I'll zero out the elements from the first row, the first column that are below the diagonal. You see, this is the first column. These are the ones below the diagonal. So what I've done is somehow, what I will do rather in step 1 is I will convert these A21 and A31 to zeros. Okay, using matrix operations. What I will do is eliminate column 1 here from R2. This is row 2. I call it R2, and this is row 3, R3, using R1, row 1, A11, A12, A13. Okay, so this is before step 1, and this is after step 1. And now, don't be confused. All these other scalars, A22, A23, and A33, these also will change. Okay, so these and these are not the same. This, for instance, this A32 is not the same as this A32 here, after we've done these row operations. Now in step 2, what I'll do is eliminate column 2 from R3. So this is row 3. And I'm going to use row 2 now to eliminate this column 2 below this R2. And there's only one column here, there's only one row here, R3. So I'm going to eliminate this A32. using R2, I'm going to eliminate this A32. Okay, these are the two steps. So the first step, what I'm doing is I'm eliminating the elements below the diagonal in the first column. In step 2, I'm eliminating the column 2 below the diagonal elements appearing in column 2. Okay, and in the process, what happens is this looks like an upper triangular matrix, right? So this is an upper triangular matrix. Okay. After step 1 and step 2, this matrix now becomes an upper triangular matrix. Okay, so let's see how we do it. In step 1, what's my goal? I want to zero out these elements appearing below the diagonal in the first column, right? Column 1. And so what I'll do is using R1. In step 1, I use R1. And the rows below R1 are R2 and R3. So I'm eliminating column 1 from R2 and R3. So let's see this 4, how do I make it 0? Using row operations. Okay, what I should do is now this is 4, 4, 2. If I multiply this first row, which is 1, 2, 2, with 4 times R1, and then subtract it from 4, 4, 2, then this 4 will become 0, right? So this is R1, which is 1, 2, 2, and this is R2, which is 4, 4, 2. So R2 minus 4 R1 is this. It gives me 0, negative 4, negative 6. Right? So this 4, 4, 2 becomes 0, negative 4, negative 6 after I do this row operation. Now let's focus on this 4 here. How do I eliminate this? Again, I have to use row 1 because I'm in step 1. And how do I eliminate this? I do this operation. I have to make this 0, right? So I multiply this first row with 4 and subtract it from this row, 4, 6, 4, and I'll effectively make this a 0. So this is my 4, 6, 4, R3, and then from that I subtract, so it's minus 4 times row 1, 1, 2, 2, 1, 2, 2. So this gives me 4, 6, 4 minus 4 times 1, 2, 2 gives me 0, negative 2, negative 4. And so this is my new row 3. And so this after step 1 is the new A. And in the new A, if you look at the first column, the lower triangular elements are zeros. Only in the first column. Okay? And in step 1, I use the first row. In step 2, I'll use the second row now. So I must make this guy 0. This negative 2 now should be 0. Eliminate column 2 from R3. This is R3. And what row should I use? The second row now, because I'm in step 2. So if I multiply this with half, because this is 2 and this is 4, right? So I take half of the R2 and subtract it from R3. So this is my row operation. What do I get? So R3 is 0, negative 2, negative 4, minus half of R2 is 0, negative 4, negative 6, 0, negative 4, negative 6, R2, and then I do this operation, I get 0, 0, negative 1. Therefore, my new matrix is this, 0, 0, negative 1. This negative 2 has been eliminated. Okay, and now this looks like a upper triangular matrix. I've not said anything about the lower triangular matrix yet. Okay, so using a sequence of row operations, I was able to convert this matrix A to an upper triangular matrix. Now, this is the general case. Actually, let's see how it looks like before we proceed to the general case. Let's look at what happens in terms of matrices. Okay, these row operations that I did in step 1 is equivalent to a matrix multiplication. So what I'm doing is I take my original matrix A, which is this guy here, and you see this sum matrix here. When I pre-multiply my original A with this matrix here, I get this matrix in step 1. Okay, and let's see how. Consider the first row here, 1, 0, 0. I'll place the 1, 0, 0 here. And so this is first row times 1, second row times 0, third row times 0. So basically, it's the first row. So this 1, 2, 2 comes here. Okay. These second row and third row are getting multiplied by zeros. Now let's look at the second row. -4, 1, 0. I juxtapose it here for convenience. So what I'm doing is I'm multiplying row 1 with -4 and row 2 with 1 and row 3 with 0 and then adding them up together, right? So what do I get? If I do this, I get 0, -4, -6. And if you look here, in this case, sorry, here, this is the second row. Now, row 2 is row 2 minus 4R1. So this is row 2 times 1 minus 4 times R1, right? This is this operation that I just did. Then let's look at the third row here. Okay, I need to implement this operation. Now let's look at this row here, -4, 0, 1. I'll juxtapose it here. So what I'm doing is I'm multiplying R1 with -4, 0 R2. So basically ignore R2 and 1 times R3. So R3 minus 4 R1. R3 minus 4 R1. And that gives me my new R3. Okay. So in effect, step 1, all I did was pre-multiply my matrix A with another matrix, and this matrix turns out to be a lower triangular matrix. Okay, and we call this lower triangular matrix M1 because we're in step 1. So what we did is the original A was replaced with M1A. And in general, that was with specific values for each element of A. Now, in general, R2, in order to eliminate A21 using A11, what we need to do is scale this row R1 with A21 over A11 and do the subtraction. R2 minus A21 over A11 R1. That's the new R2. And likewise, we take this ratio A31 over A11 and we scale R1 by that factor and then subtract it from R3 to get the new R3. And the equivalent matrix operation is shown below. So this is what we do. The values of these A's will obviously change. But what happens is I've knocked out the lower triangular elements from the first column. Now let's look at the second column. So this is A is replaced with M1A in the general case. Now let's look at the second column. Excuse me, step 2. What do we do in step 2? The lower triangular elements from column 2 is to be eliminated using R2 because we're in step 2, right? And so this is what we do. R3 is replaced with R3 minus twice R1. Excuse me, this is twice. Excuse me, sorry, this is a typo here, minus 0.5 R2. Minus 0.5 R2, not 2 R1. This is minus 0.5 R2. Okay, and this is equivalent to pre-multiplying the new matrix A from step 1 with this matrix here. 1, 0, 0 implies that basically we are repeating this row 1 here. 1, 0, 0. Row 1 times 1 plus all zeros. So row 1 is getting incorporated here. 0, 1, 0. So what does this mean is basically we're multiplying row 1 and row 2 with zeros and row 3 with zeros, and row 2 is being multiplied by 1. So basically we are taking row 2 and putting it here. So I get the same thing. 0, negative 4, negative 6, 0, negative 4, negative 6. Now here what I'm doing is, take row 3 here and I'll juxtapose it here. What am I doing? I am taking, let's ignore R1. So R3 is getting multiplied by 1, and from that we are subtracting half of this, R2. So R3 minus 0.5 of R2. So that's R3 minus 0.5 of R2. Note the typo here. Okay, and that is what we are doing, and we are getting 0, 0, negative. Again, this is a lower triangular matrix. The upper triangular elements are 0. Now, at the end, what do we get? At the end, what do you see here? This is the new A, but this is a upper triangular matrix. And the equivalent matrix operation for step 2 is this. We pre-multiplied our A from step 1 with this matrix M2, which happens to be a lower triangular matrix, and then this is our final result. And this is what we would have done in the general case. Note that these are already zeros from step 1. So what we need to do is, the scale is A32 over A22. A32 over A22. So we multiply R2 with this and subtract it from row 3, and we get the new A, where A32 is now eliminated. And this is the equivalent matrix operation. Any questions so far?
Nope.
Okay. So our A from step 1 is now replaced with M2A. So in step 1, this is what we did. This is the original A. We pre-multiplied it with M1 and got this at the end of step 1. This is the new A. And then what we did is the new A, which is actually M1A. Okay, this we pre-multiplied with M2. And then we got our result, which is a upper triangular matrix. Okay, so this is the original A. And what I just showed you is we can do a sequence, carry out a series of pre-multiplications with lower triangular matrices to get an upper triangular matrix. Okay. Now, this is my original A. Let me multiply this M2 and M1. This is what I get. M2, M1, I'll just call it M. Okay. So effectively, what I'm doing is I pre-multiplied A with this matrix M, which is M2, M1, and then I got my final answer, MA. Okay. One thing, this M2 is a lower triangular matrix. Also, M1 here is a lower triangular matrix. You can verify this yourself that when you multiply two lower triangular matrices, you will again get a lower triangular matrix. So this matrix M is also a lower triangular matrix. You see that? Upper triangular elements are 0. So the product of lower triangular matrices is lower triangular. Likewise, by the way, the product of upper triangular matrices is also upper triangular. Okay, so now this is the general case. In the kth step, what we're doing is we eliminate column K from rows Rk plus 1 through Rn using row K. Rk, so we're using, in the kth step, use Rk and eliminate, zero out the elements in the rows below Rk. So that is Rk plus 1 through Rn. Okay. And which elements from these rows are we zeroing out? Those are in column K. In other words, what we are doing is eliminate Akk plus 1 through Akn from rows Rk plus 1 through Rn using Rk. Okay. I have a illustration which will make it even clearer. So what I'm doing is this. Ri is being replaced with Ri minus, this is the scale, Aik over Akk times Rk. In the kth step, so this is, I'm using Rk, and these Ris lie below row K, so I must be K plus 1 through N. And in the case step, so that's equivalent to, in the case step, pre-multiplying matrix A with some matrix, a lower triangular matrix, MK. So I'm replacing, in the case step, A with MKA. And MK is lower triangular. So this is what's happening. Okay, so this is the matrix, initial matrix A, columns 1, 2, K minus 1, K. This is the kth column, all the way to N. And this is again the kth row, 1, 2, row K minus 1, row K. And this is, these are all rows, ith row below row K. So K, then K plus 1 until N. So this I here means anything from K plus 1 through N. Okay. Okay. Now, this is step 1. I zeroed out these lower triangular elements. Okay. And what did I use? Row 1 to zero out these from all the rows below it. Now, in step 2, I use this row 2 and then zero out these elements, which are below A22. And then this is, suppose this is step K minus 1. So what do I do in step K? This is step K minus 1. This is my step K. Now let's focus on step K. What am I doing? So before step K, these are all non-zeros, right? In step K, I'm using RK, row K, and then I converted these, I zeroed out these elements that lie below AK. K. Are you guys with me?
Yes.
Yes.
Okay. And I go all the way to step N minus 1. I don't have to go all the way to N, right? Because there's no element below A, N, N that I have to zero out. So the total number of steps required is N minus 1. And now this is what I'm doing in the general case. In the kth step, I use AKK, and then from each row below it, row I, which is below row K, so I is K plus 1 through N, what I'm doing is, this is the matrix operation, the row operation that I am carrying out. Ri is being replaced with Ri minus, this is the scale AIK over AKK times RK. Okay. That puts me in a position to write down the LU decomposition algorithm. This is only part of it, though. This is not the full LU decomposition algorithm. So another thing, now when I am, let's say this is row I, and this is row K, right? So from row K, using row K rather, I'm going to eliminate this here, AIK, right? I'm going to convert this to a 0. Now, I multiply this with this AIK over AKK, and then subtract, suppose, let's refer to this as the scale. So this I replace with this minus scale times this, right? And this guy is replaced with this minus scale times this, and I do this with this guy too, all the way until AIN. I'm subtracting scale times the corresponding element from row K in row I. But do I have to do the same operations here? I already know that these are zeros from my previous iterations, my previous steps, right? So I really don't have to do it for the entire row, only for these elements here, right? Otherwise, it will be a waste of computer time if I were to subtract 0 from 0 each time. Okay, so this is the algorithm. So input is A. How many steps do I need? 1 through N minus 1, right? This is the last step, N minus 1. So 1 through N minus 1. Then what I do is, from each row for I equals K plus 1 through N, I'm doing this. Row I is equal to Ri minus AIK over AKK RK. Okay. And this is an order n cubed algorithm. I'm not going to focus on algorithmic complexity, since some of you might not know what order notation means. But basically, now this is, each is a row, right? And each has n elements. So basically, I'm doing n arithmetic operations here. And this for loop, again, loops, actually, let's consider the upper bound, n times. So total number of operations for each iteration of the first loop is n squared. N here, and there's an inner loop, which is for n times, so n square operations. And then this outer loop is also looping n times, actually roughly n times. It's actually n minus 1 times, but we're taking upper bounds. So the whole algorithm complexity is order n cubed. And this is the equivalent operation. What I did was, when I applied this algorithm, this matrix A, each time, each step K, it was getting multiplied, pre-multiplied with some matrix MK, right? And so eventually, the whole effect was to pre-multiply this A with M1, then with M2, all the way to Mn minus 1. And that gave me the upper triangular matrix. Now, I told you that the product of lower triangular matrices is lower triangular. Okay, each of these is a lower triangular matrix, and so the product is a lower triangular matrix. So, in effect, what I'm doing is I'm pre-multiplying A with this lower triangular matrix M to get an upper triangular matrix. This is what this algorithm is accomplishing. And this M is Mn minus 1 dot 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 until M2 and M1. Okay? And M is lower triangular because each of these factors, M1, M2 until Mn minus 1 is lower triangular. Therefore, the product should be lower triangular. Now, when we do this algorithm, what are we keeping track of the M's? All we are doing is the row operations, right? And these row operations are equivalent to pre-multiplication with a matrix, right? But are we actually keeping track of the matrices? No, we are not, right? But so from this algorithm, okay, what this algorithm does is we have initially a matrix A. At the end, after all these operations, this matrix A becomes an upper triangular matrix. But we don't know what Mn minus 1 until M1 are, right? All we did was carry out a sequence of row operations. So how do we obtain this M? The solution is apply the same row operations simultaneously to A and an identity matrix I. So initially what we have is A and this identity matrix I. And then step one, what we do is pre-multiply. Basically what we're doing is some row operations, right? If we do the same row operations with this identity matrix as we do with A, then in effect, we are pre-multiplying this identity matrix with the same M1. Are you guys with me here?
Yes.
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 Then in step two, what we are doing is, now we have M1A. In step two, we do some row operations, but that's equivalent to pre-multiplying M1A with this matrix M2. Now here we have M1I, and if we carry out the same set of row operations, that is equivalent again to pre-multiplication with the same M2, right, as here. So in effect, if we do the same row operations, we are left with M2, M1I. And likewise, all the way until the last step, step N minus 1. So here, what we have done is pre-multiply whatever we had from the previous step with Mn minus 1, and we do the same row operations here. And eventually, what we get at the end of step N minus 1, we get an upper triangular matrix here, right? Which is M times A. Now, here, this is the identity matrix, remember. What is this product? M, right? The same M here. So, A, what we did is we did a lot of row operations, and eventually A got converted to an upper triangular matrix. we took this identity matrix here and we did the same set of row operations on I. And then what we get is M. Okay, so now we have both M. So what we have is M and we have the upper triangular matrix U. And what is M? M is a lower triangular matrix. Okay, now, which means that since U equals MA, A equals M inverse U, correct?
Yes.
Yes.
Okay, and M is a lower triangular matrix. Okay, M is a lower triangular matrix. Okay, so now what happens is the inverse of a lower triangular matrix is lower triangular, which means that M inverse is lower triangular. And we call that lower triangular matrix L, which is M inverse. Okay. And therefore, the whole process is equivalent to decomposing A into this lower triangular matrix L and this upper triangular matrix U. So this is basically the LU decomposition algorithm. Now the question is, okay, M inverse must be hard to compute, right? Answer is no. The matrix inversion is very hard. It involves a high complexity, algorithmic complexity, but inverting a lower triangular or an upper triangular matrix is actually simpler. You need less number of steps. The algorithm has there is a lower complexity algorithm to invert a lower triangular matrix or an upper triangular matrix for that matter. Okay?
Yes.
Okay, so this is basically LU decomposition. Any questions with LU decomposition before we move to PLU decomposition? Okay, so now let's look at PLU and Cholesky decompositions. Okay, first I'll define what's a permutation matrix. A permutation matrix is a rearrangement of the rows or columns of the identity matrix. So this is an example of a permutation matrix. All I did was, so I shuffled the rows. So R1 is this one. I took an identity matrix, I. Its row 1 would be 1, 0, 0, 0, right? And now it's in the third row. R2 actually is 0, 1, 0, 0. It's in the first row now, in the permutation matrix. R4 should have, in the identity matrix, R4 is 0, 0, 0, 1, and it's in this second row here, in the permutation matrix. Okay, so this is basically permutation matrix. It has a single 1 in every column, and it has a single 1 in each and every row. The inverse of a permutation matrix is simply its transpose. So P inverse is P transpose. Here's an example. I take this and its transpose. I multiply them together. I get the identity matrix. The determinant of the permutation matrix is 1. Now, the products of permutation matrices, you can try it out yourself, are also permutation matrices. Okay. Now, what we can do is, let's take any matrix A. What does pre-multiplying A with this permutation matrix imply? It's basically, reordering the rows of A. So this is my original matrix A, and this is the matrix P, permutation matrix. Okay, now when I do this multiplication, what do I get? I get this matrix. All I did was I have shuffled the rows of my original A. So the second row appears here, then the fourth row, and the first row is now, this is the actual first row in A, and now it's come here, and this is the third row. The third row now is incorporated here. So what does a permutation matrix do? It somehow rearranges the rows of this pre-multiplying A with a permutation matrix is equivalent to rearranging the rows of the matrix. Okay. So PA equals row reordered A. This is my A. Now, okay. Now, what is PLU decomposition? Okay. Consider this. I have a matrix A like this. What should I be doing in the first step? Using row 1, I must eliminate these from row 2, row 3, and row 4, right? Using row 1. So I must take row 2 and replace it with row 2 minus some factor times row 1. Row 3 should be equal to row 3 minus something times row 1, right? That's what I need to do. The problem is this is 0. I cannot subtract 0 times anything from 2 to give me a 0. Likewise, 1 minus anything times 0 cannot give me a 0 here. If I need to eliminate this 1 or this 2, I cannot do that because I have a 0 here. And the same thing applies to this negative 1. LU decomposition cannot be applied as A11 equals 0. In this case, what we do is we do this permutation. So what we do is we try to rearrange the rows of this matrix A. Okay, and then let's say this one here gives me this. Now I can do my, since now the first entry in row 1, column 1 is 2. I can use this 2 to eliminate the rest of that column, right? This is
Yes.
1 minus half of this 2 will give me 0 here. If I simply add half of row 1 to this, I'll get 0 here, right? So now I can carry out my LU decomposition. So what I did was I took A, I shuffled its rows, which is equivalent to pre-multiplication with a permutation matrix. And then I got this matrix, which I can now use to apply LU decomposition. Okay. Now, so this is the matrix that I get after I rearrange the rows, which is the same thing as pre-multiplying with, let's say, P prime. Let's call this P prime. And then we did the LU decomposition on P prime A. So this is the matrix. After we did all the shuffling operations, rearranging the rows, we get this matrix here, which is the original matrix A times P prime. And so once we do the LU decomposition on this, we get L and U here, which means that P prime A equals LU, right? I guess I was not clear. So I cannot carry out LU decomposition on A because of this 0 here. So what I do is I pre-multiply it with this permutation matrix P prime, and then I get a new matrix A, and then this is my P prime A, correct? And this P prime A, to this matrix P prime A, I apply the LU decomposition algorithm, whence this P prime A is equal to LU for some L and U, correct?
Yes, doctor, that's why the prime. Why not only P?
Just a notation. It doesn't mean anything.
Okay. Yeah.
Okay, this is my P prime. Okay. Now, what's the inverse of a permutation matrix? It's transpose.
Transpose.
So I multiply both sides with P prime transpose. I get A equals P prime transpose, which I call PLU. So this P equals P prime inverse. Okay. So this is basic introduction to PLU decomposition. Now, what actually will happen is if you use MATLAB, it's going to apply a sequence of permutation operations during various steps of the algorithm. Whenever it sees a 0 or even for numerical instability reasons, it will apply permutation operations. Okay, but we will just assume that everything is, all the row operations are being done at the very beginning. Okay, that's all. We'll just make this a rudimentary assumption because we don't need to know the algorithm for PLU decomposition. We just know that A is being factorized into a permutation matrix, a lower triangular matrix, and an upper triangular matrix. Okay. And we also know that if we apply a sequence of permutation operations to it, it's equivalent to a single permutation operation. Never mind all the details. So this is basically what PLU decomposition is. And MATLAB has an inbuilt subroutine. I think subroutine is called LU, or I don't remember if it's LU or PLU. I think there are two subroutines. One is LU and the other one is PLU. And they'll return PLU, let's say, then it'll return P, L, and U. So this is PLU decomposition. Questions?
I was just curious for the columns. Is this assuming that they're linear independent, like vectors, or?
So, in the beginning, I assumed that the matrix A is invertible.
Okay. All right. Thank you.
So how do we solve linear equations? AX equals B. We do this, we factorize, suppose we have this set of linear equations, and we know that A is non-singular, invertible, so we decompose A into P, L, and U. So PLU X equals B. Hence, X equals U inverse L inverse P inverse B, right? P inverse is nothing but, how do we do P inverse? Transposition, right? All we have to do is take the transpose of P, we get P inverse. And I already told you that inverting lower triangular and upper triangular matrices, the algorithm is not that hard computationally. It's not as intensive as in general in matrix inversion algorithm would be. Okay, so there are simpler algorithms to invert lower and upper triangular matrices. And so X becomes equal to this. So instead of what we're doing is, normally we would have to invert the matrix A, right? But inverting a matrix A is computationally more challenging, more computationally intensive. Instead of inverting this matrix A, what we do is we decompose A into PLU, and then we are inverting P, which is basically transposition, no big deal. And then we are applying a simpler algorithm to invert L and U. And so we get our solution X equals U inverse, L inverse, P inverse P. Okay, so inverting L and U separately is easy as they are lower triangular and upper triangular. Now, how do we determine determinant? Excuse me. How do we obtain the determinant or the inverse of a matrix A? Okay, let's see. Now, the determinant of a lower triangular or an upper triangular matrix is the product of its diagonal elements. Remember that from the previous lecture? So now what we do is, so this is the determinant of the matrix of a lower triangular matrix L. It's the product of its diagonal elements Lii, and the same thing for the upper triangular matrix. So we can use the PLU decomposition algorithm to find the determinant of any matrix A, or to find the inverse of the matrix. So A equals PLU. Okay. Determinant of A equals determinant of P, determinant of L, and determinant of U. Correct? What's the determinant of P? P is a permutation matrix. Its determinant is 1. What's the determinant of L? Lower triangular. It's the product of its diagonal elements. And likewise, the determinant of U is also a product of its diagonal elements. And so when we multiply them together, we get the determinant of this matrix A. A inverse, again, equals U inverse, L inverse, P inverse, which is, and these operations are computationally less expensive than having to invert this matrix A here. And so using PLU decomposition, we can find the matrix inverse of a matrix. Cholesky decomposition. T25, okay. Cholesky decomposition can only be applied to symmetric positive definite matrices. A must be greater than 0. Okay. This is the notation, right? So it must be symmetric and positive definite. And then the Cholesky decomposition algorithm decomposes A into this form. A equals some lower triangular matrix L times L transpose. Okay. By the way, in MATLAB, unless you specify that you need lower triangular Cholesky decomposition, what will happen is A will be decomposed into the product of an upper triangular matrix transpose and an upper triangular matrix. Okay. Anyway, so this is the standard way of doing Cholesky decomposition. I don't know why MATLAB chose to do it the other way, but A equals LL transpose. This is what Cholesky decomposition looks like. Now, L transpose is upper triangular. If this is L, this is L transpose. So basically, since L transpose is upper triangular, it does look like LU decomposition, right? A equals a lower triangular matrix times an upper triangular matrix. So it's a special case of LU decomposition. where the upper triangular matrix is nothing but the transpose of the lower triangular matrix. And this Cholesky decomposition is only applicable when A is positive definite, symmetric positive definite. So this is what MATLAB actually does. It factorizes A into U transpose U, where U is an upper triangular matrix. Okay, now what are the benefits of PLU decomposition? What do you think are the benefits? You can see one clear benefit, half the storage space, right? You don't have to store L and U, right? So it's basically L and L transpose. You don't have a separate L and a U. So 50% less storage space. Now, pivoting is not necessary. By pivoting is, when we do PLU decomposition, sometimes we have to swap rows. That's called pivoting. Okay, so that's not necessary for Cholesky decomposition. And it also is quicker. Takes approximately 1/6 n cubed steps, whereas LU decomposition takes 2/3 n cubed steps. So it's much faster. Okay, so these are the benefits of LU decomposition, but it can only be applied to a symmetric positive definite matrix. Now, consider this little lemma here. We'll end this lecture with this small observation. Suppose a matrix A can be expressed in this form, B times B transpose, where B is some other matrix. So there exists some matrix B such that A equals BB transpose. Then A is positive semi-definite. Proof: A is BB transpose, right? Now, what is the definition of positive semi-definiteness? X transpose AX should always be greater than or equal to 0, right? So for any X, vector X, let's do X transpose AX. It's equal to X transpose BB transpose X, which is equal to B transpose X whole transpose. I took the first two factors here, X transpose B, and then I express it in this manner, and then I have B transpose X. This is B transpose X is some vector Y, some vector, right? And so let's call it Y. So this is Y transpose Y, some vector transpose times that vector itself, Y transpose Y. Okay, and this is basically the squared L2 norm of B transpose X, right? So it has to be greater than or equal to 0. Okay, which shows that A is positive semi-definite. Now, in Cholesky decomposition, we are factorizing a positive definite matrix into this one, LL transpose. So it's a special case. Instead of BB transpose, we have LL transpose. And at least from this lemma, you can infer that A is positive semi-definite in order to apply the Cholesky decomposition. But in reality, it'll only work with when A is positive definite. The MATLAB command to carry out this Cholesky decomposition is, I think it's just CHOL. Any questions?
No.
Okay, so just a quick recap. A equals LU decomposition. In the step K, we eliminate column K from rows RK plus 1 through row n using, and this is the kth step, and we carry out it for all rows I equals k plus 1 to n. And so in effect, what we are doing is we are pre-multiplying the matrix A with a sequence of lower triangular matrices, and that gives us an upper triangular matrix. Whence MA equals U. These are all lower triangular matrices, and their product is M, which is also lower triangular. So MA equals U, whence A equals M inverse U, right? Or since the inverse of a lower triangular matrix is also lower triangular, in effect, what we have is A equals LU, where L is M inverse. Product of lower triangular matrices is lower triangular. Inverse of a lower triangular matrix is also lower triangular. Product of permutation matrices is a permutation matrix. Inverse of a permutation matrix is its transpose. Determinant of a permutation matrix is 1. And this is PLU decomposition. What we do is we rearrange the rows of A, which is equivalent to pre-multiplying it with P prime, where P prime is a permutation matrix, and then applying Cholesky decomposition. So P prime A equals LU, whence A equals PLU, where P equals inverse of P prime. And I just explained how we can easily, from the PLU decomposition of a matrix, we can obtain the determinant of a matrix and the inverse of the matrix. Cholesky decomposition is of this form. It's only applied to symmetric positive definite A's, and it's LL transpose or U transpose U. Any questions?
No, it's clear.
Okay, so see you guys on Thursday, and see you guys on Thursday. Now, I wanted to give you the deadline today, but it'll be next week. All of next week you can work on it, and the Monday after that, okay, is the deadline. I'm just telling you, and so work on it. I'll put it online. I wanted to put it online today, but I need some help. That's why I couldn't. I'll do it tomorrow. Okay?
Okay.
Thank you, Dr. Das.
Okay. See you guys.
Thank you.
Thank
See you.
you.